Hello everybody, my name is Philip Sibson. I'm from Bristol University and today I'll be talking about my colleagues and I's recent work on network quantum secured communications with handheld and integrated devices. So this work is supported by the UK Quantum Communications Hub led by the University of York, and today I'll summarise a lot of Bristol's efforts in this area. We want to provide a sort of holistic framework for secured networks at all scales. This includes handheld devices for short-range free space applications for consumers, such as a quantum ATM. We have a package of work that motivates the use of integrated photonics for QKD, shows how using this platform can play a large role in their increased adoption. And then I'll discuss how they can be used in metro scale and long-haul networks, and specifically how the security can help the next generation of software-defined networks. So I'll first look at short-range free space QKD technologies led by David Lowndes and John Rarity in the audience. Our goal here is to advance a previous demonstrator of a consumer QKD device that was developed by Bristol and HP Labs. Here, our system is called a quantum ATM. It comprises of a large receiver unit, as well as a low-cost handheld device for consumer-level commercial and defense applications. In this example, we envisage many credit card scale devices being handed around to users, and widely distributed quantum ATMs, which could be placed at the nodes of each one of these metro scale networks, allowing you entrance into this network and to establish keys between different parties. The first generation of these devices were illustrated in the top row. It was based on 4 patterned LEDs with a glass polarizer in front of it so that you could select each one of the BB84 states. A pinhole was used to minimize some of the multi-mode channels that could be output, so to minimize eavesdropper attacks. And it was based on a magnetic docking station with a large receiver unit next to it. The second generation of this was to miniaturize the transmitter further into a credit card scale device with a flexible bob receiver. The pinhole in this case is replaced with a curved fiber to dissipate these multi-modes to transmit out on a single path. So we're now using a credit card slot device instead of this magnetic base to align the optical channels. This is so that it can be cheaper to manufacture, but also provide an acceptable and repeatable docking station performance. This can be coupled with active alignment, such as the research that's happened at the University of Oxford. And in this particular system, there was optics to correct for polarization, dispersion, and misalignment that occurred throughout the fiber. This produces 4% quantum bit error rate, 2 nanosecond full width half maximum pulses at a rate of 100 megahertz. Here's an illustration of the flexible bob unit, a 19-inch rack-mountable unit with separate optical and electronic modules. This enables upgrades as well as multiple protocols to be implemented. The classical communication can be done over a public channel, such as Wi-Fi, and the transmitter device has USB interface for laptop and phone connections. So this allows you access to a metro scale network, but for most metro scale and most long-haul networks, we actually need to be communicating over fiber optics. And this is where we want to use systems based on integrated photonics to provide extra benefits. So the integrated photonics platform is analogous to the microelectronics you find in your phone or in your laptop, and it can provide the same sorts of benefits. It's miniaturized, so we can have portable or field-deployable devices. It becomes possible to create large and complex circuitry to add extra functionality. And it's a platform that's amenable to mass manufacturable, so it can reduce costs for personal use. So we wanted to demonstrate that you could use this in chip systems, so we generated an experiment for the first chip-to-chip quantum key distribution devices. This is using commercial fabrication facilities, and in particular, an indium phosphide transmitter and silicon oxynitride receiver. We demonstrated clock rates, secure key rates, and quantum bit error rates comparable to the state-of-the-art. And we used the complexity available in these circuits to implement multiple protocols for communication. We've been working with the National Physics Laboratory to certify and calibrate these systems, but we also wanted to illustrate the practical advantages that this platform could provide. So I'll now discuss wavelength division multiplexing. So one of the limiting factors in QKD, or the adoption of QKD, is the low secure key rates compared to normal commercial traffic. So one approach to overcome this limitation is a brute force approach to multiplex multiple channels onto a single transmission fiber. So here we illustrate this protocol with wavelength division multiplexing. But when it comes to current bulk and fiber implementations, doing wavelength division multiplexing on a large scale becomes a bit infeasible. You have to make many copies of the same system, and you have to make them independently. In the integrated platform, though, it's much more suitable. You can create many copies of the same device on a small footprint monolithic chip without significant increases in overhead or costs. So in this experiment, we demonstrated 2 channels of biased bases BB84 decoy states to demonstrate that we can increase the rates, effectively doubling our rates, and minimizing the increase of error due to crosstalk through wavelength and temporal filtering. We're moving towards larger scale demonstrations of this system, as well as increasing security through protocols such as measurement device independence. So we've seen how we can use this platform to get a number of advantages, but if we really want to take this to the extreme, we need to move towards silicon photonics. Silicon photonics is a world-leading platform for quantum technologies, and it provides greater benefits of even more miniaturization, better cost-effective manufacturing, but also integration with common electronics. So our first demonstration of using this platform was involving entanglement distribution between chips. Silicon provides a high nonlinearity in the material, which means that we can generate single pairs of photons through spontaneous 4-wave mixing. On chip, we use path-encoded systems, as it has a great level of stability and high fidelity in encoding. But if we were to communicate over path, we need 2 fibers, and all of a sudden, the slight different path lengths between those fibers, the variations due to temperature, would lead to fast rotating frames of reference, decoherence, and all sorts of problems. So in this particular example, we converted that path-encoded system to a polarization output for one of the single photons. That was then sent to a second chip so that we could demonstrate this entanglement distribution, one of the basic building blocks needed for a lot of quantum communication applications. However, this technique was using slow thermo-optic phase shifters to prepare the states and to measure the states. This is very good for high precision measurements, but it's not very good for high speed modulation of quantum states, the sort of thing that we need for proper telecommunications. So here we overcame the limitation of this speed by combining slow but precise thermo-optic phase shifters with fast but non-ideal carrier depletion modulators. You're able to come up with a particular way of working by using DC biasing and AC small-scale signals for pulse modulation in coherent one-way between chips, as well as for the 4 BB84 state preparation in both polarization and time-bin encoding. So we used this demonstration to show that standard silicon photonics as a platform can still be amenable for high speed and low error rate quantum key distribution. But we wanted to take this further, so we also demonstrated other technologies, such as quantum random number generation. Random numbers are essential in many fields, such as cryptography, and they are a subsystem of a larger QKD system. By amplifying the vacuum state noise through a homodyne detector, we're able to get improved rates and cost of implementation for these quantum random numbers. We use standard photonic technologies, such as photodiodes, to measure a continuous variable. So this provides a string of random numbers per measurement. By implementing this on silicon, we were able to demonstrate 11 dBs of signal to noise, a 3 dB bandwidth of about 150 megahertz. And this produces 1.2 gigabits per second of post-processed quantum random numbers that pass all of the sort of standard NIST test suites. So this demonstrates that you can use the integrated platform to create chip-based quantum key distribution systems, benefiting from the cost-effective manufacturing, the low size, weight, and power performance that we can get, as well as a route to enable large-scale deployment of these sorts of systems. But now we want to actually deploy these systems across metro-scale networks and long-haul networks to show how QKD can actually benefit new paradigms of working, such as software-defined networks. At Bristol, we have access to the Bristol is Open Network, or BIO network. This is a metro-scale network of 5 nodes with 144 cores of fiber in between each section. And it can be used as a testbed for generating the next generation of network paradigms. So we've been characterizing and deploying commercial QKD systems across this network to demonstrate the core functionality. But this is also connected to a national dark fiber infrastructure, so that there are connections between Bristol and London, and then our collaborators in the Quantum Communications Hub, Cambridge and Toshiba, are extending this further between London and Cambridge. We'll be connecting up 2 metro-scale networks to provide the first quantum UK backbone network. So one of the new architectures that we want to employ is called software-defined networks. And it's already being deployed on Bristol is Open fibers by our collaborators, the High Performance Network Group at Bristol. With SDN, software-defined networks, the network is programmable through software applications. And this allows you to centralize a control plane and decouple it from the data that's actually being transmitted around the network. This allows for flexible network assignment and resource management, depending on dynamic user requests. So it provides a real flexible framework in which you can work. In the BIO network, each node contains transmitters, receivers, optical switches, amplifiers, and wave shapers, all controlled by servers. And this provides you to extract away from the actual physical implementation, provide logical networks, much like an operating system does with a computer. And we can actually benefit from using this sort of approach for QKD. We can adapt the techniques that are already being used to make a quantum-aware software-defined network, ones in which pathfinding algorithms can be adapted to incorporate the constraints that are unique to quantum key distribution. We can optimize for things like secret key rate and minimize latency, as well as manage the key as an effective resource by adapting the routes that are taken based on eavesdropper detection events. And we actually have a little prepared earlier video that demonstrates this working. So although it's on the same screen, these are actually 2 instances of a program called QTunnel, made by our software engineer, Rich Collins, who's also in the audience. And these are 2 different entry points to the Bristol is Open network, with a program monitoring the communication between both. So hopefully this will play. So the program creates a network tunnel by sharing keys between 2 different QKD devices, connecting them through software-defined networks. The server at the first node of BIO is started with another node connected to the first. So a new tunnel is then created between the 2 of them, and a software-defined network has calculated the connections and established an optical path between the 2 devices. The key then gets exchanged between the 2 users, and in this particular example, we use that key for GCM AES cipher to encrypt sensitive data that is input at the terminal on the bottom. So we're just writing in some message at the bottom, and that's about to transfer over to the other terminal of the other entry points of the network. The unencrypted data can be recovered, but this monitoring software in the middle is supposed to show that it's actually encrypted on the network, so that it's just gobbledygook going out in the middle there. So this highlights how the software-defined network connects the 2 different QKD devices, how requests are made to that software-defined network controller. But the keys that are established can actually be used for any form of application that you so wish. For example, we've talked about this centralized controller that talks to various nodes around the network, as it does for another related concept called network function virtualization, or NFV. Well, this control plane is actually a really vulnerable area of the network, and